Okay, so welcome to phase 4, everybody. I do want to start with a overall intro to what this phase is going to be all about. I personally like to think of this phase as kind of like an electives phase, where at the end of the phase, you're going to do one of 4 quite different projects. So you can see over here, in order of curriculum appearance, the project will either be a recommendation system, a time series forecasting project, natural language processing. So those of you who've been wanting to work with words, here's your chance. And we're going to work with a neural network to do image classification. So these are the 4 possible projects that you'll choose from, and you will do only one of these at the end of the phase. So most people who go through this phase successfully, I think, is to pick 1, maybe 2, to go through in depth. And then the other 2, because you do have access to Canvas and you will have, you will be able to like download all of this stuff before you graduate, you can go through the other 2 later. I mean, I still recommend that you come to study groups, and just so you can, have all of the information absorbed while, we're talking about it. But for the most part, I think that the most successful students focus on 1, maybe 2 out of 4 of these topics. But yeah, I'm going to go over really briefly what each of these are going to be about and kind of what the project is, so you can have an idea of what you will be working with. Like right now, just so you can get an idea of what to start to focus on. If any of you have a specific topic that you know that you're going to be more interested in than the others, great. For those of you who don't, maybe you can use the project topic to kind of guide what you decide to focus on. And of course, know that right after phase 4 leads into our capstone project, which is going to be 8 weeks of just working on a single project. Embedded in that 8 weeks is the ability to go and brush up on some of these other topics as well. So maybe you can take that into consideration as well. Okay, so if I take a look at the phase, here I like the phase for content over here, and let me go into student view so it looks like what you will see. Click over here. All right. So we have how many topics? I think it's exactly 10 topics, and I'm going to talk about each one. So we start with actually 3 topics that are neither, or not neither, but that are none of the project topics, but these are small topics that could be useful. So today we're going to talk about principal component analysis, and tomorrow we're going to talk about clustering. Both of these are actually really interesting to incorporate with some of the projects that we're going to do or have already done. Later when we talk about Pca, I'm going to show you all how you can incorporate Pca with, for example, the project they all just did with the phase 3 project. Clustering is another one. Clustering, I think I've mentioned a few times when I talk about unsupervised learning, how you can kind of group your data. I'll talk more about that tomorrow. Next week, we have big data and PySpark. So another one of these like little topics, but pretty much PySpark is a way that you can work with big data. And the things that you can do in big data are pretty much the same as the stuff that we've already been doing, just in a slightly different syntax. It's in a completely different language, different environment. And we'll talk about that next week. We'll get to recommendation systems. For this one, the project will be doing a movie recommendation system. That's the data that's provided. If you're interested in doing a different data set, we'll talk more about that when we get there. After that, we'll hit time series. Now, time series, the project that's provided is real estate price forecasting. So if you're interested in that, that's what the project is. There will be 2 topics on time series. Then we have natural language processing, and this project is classifying whether a tweet is positive or negative in sentiment. And I believe the data set is on, it's on the South by Southwest conference of like 2012, but I'll show you all how to get additional data if you would like. Finally, neural networks. Neural networks is 3 different topics, and the project is predicting whether an X-ray scan shows signs of pneumonia or not. So those are the project topics. Those are project topics that you'll be able to choose from at the end of the phase. Now, there's one more topic at the very end, operationalizing code and AWS. Now, this topic I will not be doing a study group for, because if you actually go into one of these, it pretty much links you to the Amazon tutorial for setting up AWS and things like that. Now, when we get to the capstone phase, I'm going to be going over some more direct applications of AWS, for example, like setting up a database, how you can host your data and information on AWS. So I'll talk about that during the capstone phase. So this is more of like how you can run like a Jupyter notebook on AWS. So feel free to work through that. I would say not a priority for this phase, to be honest, but the lessons are here for you. This phase especially, because the idea is to deep dive into one of these topics, the appendix is actually a really, really good place to further those deep dives. So you have time series appendix, which I will talk about when we get to each of these topics. Graph theory, not so much. Convolutional neural networks, this is basically what you would use for images. Transfer learning is also a neural network thing. Deep NLP, basically, if you want to talk about more advanced natural language processing. I'm actually going to go through a couple of these during a neural network, during a NLP study group as well. So I'm going to hit some of these during a study group. So I do definitely recommend this if you're interested in text data. And finally, we have our project. With that, the calendar is over here. I do think I might rearrange some of the topics so that we get introduced to some of the topics earlier on. For example, like neural networks, we won't hit until like week 5 or 6, and I do want to move maybe one of those earlier. So keep tabs on here. I'll also mention in the Slack channel if I do decide to shuffle anything around. But with that, any questions about this phase? I know there's a lot of information, and a lot of the stuff is like we haven't really seen directly yet, but yeah, any thoughts about what we're gonna embark on over the next couple of months?
Okay, one thing is it, I'm not saying I'm not going to come to any of the sessions, but I am saying if I focus on like NLP, like that's what I want to do, like could I like do that and then also like kind of get a head start ahead?
Yes,
and then like
100%.
kind of like ignore the other stuff until I get to it.
Yeah, absolutely. I mean, I do encourage that. I also like you all to get a head start on the projects anyways. So yeah, definitely if you know you want to focus on NLP, or if you already have decided based on, I guess, everything I've said up till now, what you want to work on, you can start looking at the material. I still do recommend that you come to study groups just so you know information.
I'll be here. Don't worry. I'll be
here. Yeah, but I mean, yeah. I'm not going to stop you from working on your project, and I'm more than happy to talk about it during one-on-ones as well. All right. Any other questions? All right. If there's nothing else, let's get started with phase 4. The first topic for phase 4 is PCA. And PCA stands for Principal Components Analysis. And we're going to do a quick overview of what unsupervised learning is and what exactly PCA is about. I think some of you might have encountered it in some of your research during your phase 3 project, maybe. Why we are going to do PCA, how does it work? And we're going to talk about evaluating it as well. And in this slideshow, there are only like 6 slides in this presentation because PCA is kind of like a small part of the machine learning process, but I'm going to talk about how you could incorporate this into your projects. So what is unsupervised learning and PCA? So I think I've talked about this a couple times. The distinction between supervised and unsupervised learning, we're going to go a little bit more in depth tomorrow. But basically supervised learning is what we've done so far. The last 2 projects that we've worked on, machine learning projects, both of them, are making predictions on something. You're either predicting a continuous variable, that was phase 2, that was regression, or you're predicting categories, you're doing classification. That is, categorical data. So supervised learning is done to predict on labeled data. All of the data that we use to train our model already had associated labels, whether it is the categories that we had or the housing prices that came with our data set. That teaches our machines to understand the relationship between, our features and our target. In unsupervised learning, there are no labels. So I always talk about clustering as the first example because clustering is just, grouping your data. If let's say you have, let's not even use something that let's say we have, I don't know, let's say we have a bunch of tweets, for example. We're not even going to think about how we process text data yet, but if you think about tweets from different people, there are many different ways that you can group tweets. So perhaps based on maybe something simple like language of the tweet, maybe you can group your tweets based on region or language, things like that. Or maybe perhaps based on the content of the tweet, you can classify people by things like age group, demographic, so on and so forth. And these tweets aren't necessarily already labeled, but you're using features of the tweet to help group things together. We'll talk more about clustering tomorrow. PCA which is what we're going to talk about today, is also an unsupervised problem, and we'll walk through what that's all about in a little bit. And LDA, which is actually very similar to clustering. I'll bring it up tomorrow in a little bit, but we'll go more in depth into what LDA is when we talk about NLP. So Pca is one type of dimensionality reduction. Now, dimensionality reduction, that whole umbrella term, is unsupervised learning. So Pca is just one example of dimensionality reduction. There are a couple other types as well, and later in a couple of slides, I have links to documentation as well. But basically, dimensionality reduction is, let's just say you have a data set with 1,000 columns, which actually if you like zoom out, look at the big picture, is not that many, but let's say you have 1,000 columns and it's taking a long time for your models to train on your local machine. One thing that you could do is reduce the dimensionality of your data set from 1,000 columns to maybe like 10 columns, and then run your model on 10 columns. How that is done from 1,000 to 10, we'll talk about that in a little bit, but that's literally what dimensionality reduction is. You're removing, or not removing, but you're lowering the number of columns that exist in your data set. Now, it is unsupervised because all we're telling it is how many dimensions to reduce to. So for example, from the example of going to 1,000 to 10, I'm just telling my model, I want to see 10 features out of 1,000. And what happens is each feature ends up being a linear combination of your 1,000 features. So for example, our new feature 1 is going to be like 0.5 times feature 1 plus 1.5 times feature 2 plus, I don't know, 5 times feature 3, so on and so forth. Each of the new features is a linear combination of your 1,000 old features. And then also, each of these new features is called a principal component. That's why this is called Pca, Principal Components Analysis. So all you're telling it is how many dimensions you want. Pca reduces the dimensionality of the feature set into n principal components, which is how many features you want, while maintaining its variance. So that is what makes Pca very, very unique compared to all of the other dimensionality reduction techniques. These techniques will optimize for different things. And for Pca, what it's optimizing for is overall variance in your data. And that makes it very, very helpful because if you're trying to look at the relationship between, let's say the price of a house and like 1,000 features of the house, you're trying to maintain the relationships as much as possible, but with fewer features. So if you think about it, let's say, okay, in a house, you have things like square footage and the number of floors, right? And square footage and number of floors, I think if y'all remember from that data set, are pretty related to each other. You know, the more number of floors you have, the more overall square footage you have. What Pca will do is, okay, since these two have kind of a similar relationship, in my new principal components, I don't need to consider both these features as strongly, if that makes sense. So it kind of in some way removes some redundancy in your features, but also maintains that, okay, I still want to keep the fact that price does overall increase with square footage. Therefore, maybe I'll do like 5 times square footage plus 0.01 times number of floors. That's not a factual example, but it's a way to show that Pca is making these more efficient and also reducing redundancy, which I guess are kind of the same thing. And I talked about this before. Principal components are linear combinations of the original features. A lot of facts there. Any questions at this point? Okay. So next, why and when do we use Pca? So there is this thing known as the curse of dimensionality. That's actually a pretty commonly used phrase in the data science world when you have a lot of features. So as we have more features, data points become more sparse. One really quick way you get a lot of features is, for example, when you one-hot encode your data, or when you do like a get dummies, you end up with a lot of zero values. So you're actually not really storing that much information, but you still have a lot of that, those zeros taking up space. Later, when we get to text data and image data, that curse of dimensionality gets even bigger. So if you think about text data, I think I've mentioned this a couple times, that when you deal with text data, one way that you can look at text data is every column represents a unique word that appears in your data set. So very, very quickly, you can imagine that your data sets are going to be like tens of thousands of columns long. So as distance between your points get greater, it makes it more difficult to implement some machine learning models. So some of you have already seen that with your phase 3 project, machine learning models were taking a very, very long time to run. For the couple of you that I've seen this week already, I like ran an SVM model for 3 days this past weekend because I dealt with like 200 columns and like, I don't know, like 200,000 rows, and an SVM model took 3 days to run. So Pca is actually most commonly used in conjunction with SVM. In conjunction with SVM. I'll talk about that a little bit more later. So in terms of time and space complexity, Pca does help your models run more efficiently. And because it is maintaining overall variance in your data, you're trying to not lose as much information. I'll show you all a graph that kind of will depict what that means. So when to use Pca, typically when you have a lot of continuous features. Pca doesn't work super well when you have categorical features, but there is an option for categorical features. I'll show you all that later. And it's also really good for clustering or computationally heavy ML algorithms like SVM. So the idea of lowering dimensionality but maintaining variance works very, very well for SVM because you're maintaining variance. So you're maintaining the way in which your data is spread across your feature space, but in fewer dimensions. And SVM is a model that, tries to take a hyperplane and divides your data. So when you have fewer dimensions to try to divide your data across, yet your data is still as spread out as it was in 1,000 dimensions, makes it a lot more efficient. So typically, if your SVM models are taking very, very long to run, Pca is a good thing to implement. You can actually implement Pca as part of your scikit-learn pipeline as well. I know some of you who had to run long models are like not happy about this because y'all had to wait hours for your models to run. But yeah, Pca is a phase 4 topic, so sorry about that. Any questions about this slide? Okay, so let's get into how Pca works. Now, I think that in our entire curriculum, the math of Pca is probably the hardest math. And there is, I think there is one lab that has you implement Pca from scratch, which honestly, you will probably never have to do. But it's good to know roughly how Pca works. So mathematically, principal components are found through doing Eigenv Decomposition of the covariance matrix. That's basically a linear algebra process. Excuse me, tickle my throat. So it's basically a linear algebra process. So the steps to that, actually before that, let's talk about Eigenv Decomposition. Eigenv Decomposition is not super important for us to know, but in the math world is something that helps you make sense of your data. So Eigenv Decomposition basically means that when you have some sort of matrix with a bunch of numbers, which is basically how our data is presented, right? We have rows and columns. When you do Eigenv Decomposition, it's a way of reducing the redundancy in your data set. And then also normalizing your data set as well. So that's why when you look at your principal components, after you transform your data, the data is usually fairly centered around 0. So the steps to that, first you're recentering your data such that the means of each feature are 0. Basically, you can do something like standard scalar, and that's a method of recentering your data. Next, you have to get the covariance matrix, basically df.cor. You all did this in phase 2. Then you have to get the eigenvectors of the covariance matrix. Now, what eigenvectors represent? Eigenvectors basically represent the least redundancy possible, but also the span of which your features take up space, if that makes sense. So let's say that your feature set spans, what's a good way to put this? So let's say if you have one feature that is an exact multiple of another feature, that will not be represented twice in your eigenvectors. That detail is not super important, but that's what that is. Then you're sorting your eigenvectors, and then you're multiplying it by your recenter data so that you get your principal components. Again, the math of this is not super important, and I know I'm using a lot of mathematical terms here, but for those of you who have come across any linear algebra, you might have come across eigenvectors, eigenvalues. That's what this is. So actually, when you do this process, you end up with the number of eigenvectors that matches the number of features that you had at the start. And because you're sorting your eigenvectors, you just have to take the number of eigenvectors of principal components that you want. So let's just say I had 1,000 features to start with. At the end here, when I have these eigenvectors, I actually have 1,000 of them. But if I just want to take 2 principal components or 10 principal components, I'm just taking the first 2 or 10 columns in that new data set. Questions about this? All right. Again, math of this, not the most important thing. I think implementation of this is much, much more useful. Okay. So dimensionality reduction for visualizations. Pca, I think, is a great way to produce visualizations of high dimensionality data sets. So this is an example actually from one of my old student projects. I think I've shown this project a few times, but this is, I think, I want to say at least a couple thousand features that I've PCA'd down to 3 dimensions. So this is the data in 3-dimensional space, but it is still representing information for all couple thousand features that it originally had. And this was a classification problem. So red is one class, blue is one class. And based on this, I talked about the separability of data when we talked about classification before. With a visualization like this, and I think this was initially done in Plotly, so I should have rotated it in a better way. But you can sort of see that there is kind of a clear distinction between the red zones and the blue zones. And so anything red should be one class, anything blue should be another class. This is a good way of just looking at your data separability overall, rather than just picking out 2 or 3 features to display your data over. So if you're looking at a classification problem, Pca is a really, really good way to look at the separability of your classes. And you can do this in 3D, 2D. Yeah, actually, those are the only ones because that's all we can see. But yeah, this I think is a really, really sweet EDA graph to have. So in terms of the different kinds of dimensionality reduction methods, there are some that are preferred over others in different scenarios. So the most commonly used one, especially if you're using this as a part of your modeling processes, regular Pca, the one that I've been talking about, is over here. And I do want to show you all the documentation real quick. The only parameter that you really have to play with is the number of components that you want. So basically, if n components is not set, all components will be kept, but it will be in its eigenvectors. So most of the time, you'll set something that is much smaller than your original data set. So with this n components, you just have to instantiate Pca with a number. So I think they should have an example over here. Let me zoom in a little bit. When I instantiate Pca, I have Pca of n components equal to 2. So that means I want 2-dimensional data. And then I fit it on my x. You should actually not do just fit, but there's also fit transform here. There's fit transform, or you can do fit and transform. And the idea of data leakage, if you're using this for modeling, also will apply. So if you're doing this as part of your modeling pipeline, you'll do your fit transform on your train set and then just your transform on your test set. If you ever needed to, you can also inverse transform your data back into its original form because it is linear combinations. Cool. So in terms of the, let me see if there's an example over here. I guess there's not one here, but you can pretty much implement Pca as part of your scikit-learn pipeline as well. So basically the step right before modeling is usually where people put Pca. All right. Some of these other methods, there's truncated Svd. If you have more categorical data, truncated Svd is better. It's a little bit more efficient as well. And then finally, there's this other one called TSNE. People call it TSNE for short. And TSNE is completely different from Pca, not completely different from Pca, but it optimizes for something slightly different. How I talked about Pca optimizing for variance, TSNE actually optimizes for separability. We don't go into the math of TSNE too much, but if you ever needed to make a visualization, this one was made with Pca, but I think it would have been a little more clearer to use TSNE. Questions at this point?
Good question. So realistically, if you don't, I mean, what's the whole point of picking the component Pca? Because aren't we just basically trying to reduce the dimensionality? We can't really see anything besides 3 dimensions, right? We couldn't graph anything. Oh, okay, so just wanted to know why they let you pick it. Just didn't make sense to me.
Yeah, usually if you're doing it for the purpose of visualization, 2 or 3, but if you're using it in your modeling, And I'll show you the next graph is actually when you sort of tune PCA. If you want to make your models just work more efficiently and you have like 1,000 features, you don't want to cut it all the way down to 2 because you might still lose some information. So maybe you do something like maybe 5 or 50, depending on how big your data set. And I'll show you the next graph. That's actually what will answer your question, actually.
Okay, thanks.
Of course, of course. Oh, one more thing to mention is that when you do PCA, one big downside of it is that you lose interpretability. Each of your principal components will just be random numbers. And because it is a linear combination of a bunch of features, yes, you can actually go in and figure out what the, let me see, where's the attribute? You can sort of see, oh, where is it? Okay, I forget where it is currently, but you can actually figure out the makeup of each principal component. I believe it is it in here, get params? No, not params. Somewhere here, oh, here, let me zoom out a little bit. If you get the components, you can actually see what the linear combination of each feature is if you really, really wanted to interpret your PCA. But by itself, PCA becomes a lot harder to explain. Like even if you were to put it through a random forest and then you have, let's say, 50 principal components, you have your feature importances, it's just going to show you like PC5 is the most important feature. And in order to figure out what actually is the most important feature, you would have to go into PC5, look at what the makeup of that is. And sometimes that is not necessarily the most, it's not usually a very conclusive way, or your results are not always very conclusive when you try and figure out important features looking at PCA. So that's one big downside. But if your idea is, if your goal is to be efficient and quick with your modeling, PCA is great for that. Okay, so this seemingly simple graph will answer Sam's question from earlier. How many principal components is best for your data set? So this is in terms of when you want to use PCA to speed up your modeling. So let's just say that this data set started with 65 features. We have something called explained variance. So if we actually look over here, we can get the explained variance by each, the amount of variance explained by each of your selected components as a percentage of your original variance. So overall, in your 1,000 dimension data, there was an amount of variance that occurred across all of your features. And if you want your principal components to maintain as much information as possible, you want to maintain as much of that variance as possible, because it is all about the changes between features and, the changes between features and target that is useful for modeling. So if we look at this, usually if you're trying to figure out, okay, how many principal components is good enough, you would plot a graph like this, where you have the number of components on the x-axis and the percentage of explained variance on your y-axis. Now, the fewer principal components you have, the less explained variance you have. So what that means is, let's say I stop over here, and let me annotate this real quick. So let's say I stop at like 5 components. At 5 components, I'm only maintaining roughly, 55% of my explained variance. So I'm actually losing 45% of the variation in my data that I initially had. If you actually think back to when we dealt with regression, R squared was literally telling us how the proportion of the variance that is explained by your features. If we get rid of that variance, your model will have less to explain, if that makes sense. So typically you would look at this and figure out, okay, how much variance is really enough? Sometimes you are constrained by the computational power that you have. So sometimes your model will be like, okay, I have to max out at like 30 components. Then, okay, you have 30 components. But if you have a little bit of flexibility there, maybe see where you have like 90 to 100%. Typically, I think 85 is a good benchmark threshold for the minimum number of principal components. So for this case, I could take my data and stop it at, what's this, maybe like 18 principal components and still get a fairly good model going. But, if you can afford to, let's say we stop at 40, we have almost 100% of our variance maintained. So I would just set it to 40 components. But, what's the big difference going down from 65 to 40? For some models, it means a lot. Some models, not so much. So really depends on what you're working with. SVM will see the greatest increase in efficiency with fewer components, something like any tree-based model. Typically, if there's a feature with not much variance anyways, it won't even look at that. So the improvement will be kind of marginal unless you're cutting down a lot of features. But yeah, that's PCA. Any questions about anything I've talked about? This is my last slide. Any questions about anything at all?
This is okay. So this is something just I'm kind of breaking it down. 'Cause I'm not that smart, but like breaking like, is this something that you would do, like you said, to like reduce dimensionality, but basically to like once you, I guess, run a model, right? Like, would you do it just to reduce time, or is it something that you would use to like improve, like
typically,
to improve a model?
Yeah, typically, PCA won't improve a singular model's performance because PCA is you're losing information every time you do PCA. I can see how it could help any model that does resampling of your data. For example, like in random forest, where you're bootstrapping for each feature and for each feature for each tree as well. The features that you're choosing from will all be a little bit more informative. So I can see how it could help models like that. But for the most part, it's not really so much to improve performance, to improve model metrics, but to improve efficiency.
Okay. All right. Cool. Thank you.
Yeah, of course. Anything else?
Tying like that variance bias trade-off kind of to this, how do we know at what point, like what's a good amount of features to, like, do we just have to keep running it like repetitively, like, and letting it, you know, say this like the optimal amount of loss in the scenario of explain variance for these features?
That's a good point. So typically, if you are running at something that's very close to something that's fairly close to 100% of explained variance maintained, you should see model performance be very, very similar to what you're already getting in terms of your metrics. Now, if like 42 features is still too much, what I would do is lower it first. And let's say I go down to 20 and take a look at how your metrics are doing. Sometimes losing these 20 extra features will not hurt your model very much because most of the variance is going to be contained in the first few principal components. Like you can see that going from like 1 component to 2, and this is just roughly estimating, your variance increases by much, and the marginal improvement or the marginal increase in the amount of explained variance kind of plateaus off. So you will get the most bang for your buck using the first few components regardless. Every additional component you add will have a diminishing, diminishing return on your metrics. If that makes sense. but yeah, if 40 is still too much, I would actually try lower, see how your model metrics improve, if at all. If it doesn't get worse, keep it at 20, because why have your model run like 20 extra features if you don't have to?
Got it. And so in regards to using PCA, I know I've seen it used in like SVM, logistic regression. Is there any limitation on what like machine models we've learned that we can't use it on? Like, could we use it on k-nearest neighbors?
It can be used with any machine learning model, because when you use PCA, you're reducing the features, and everything is going to be numerical still. So you're not limited, as long as it's still in a data frame, you don't have null values, which just will not give you any null values, you're all good to go. The downside is really you lose that level of interpretability. Like if you do your feature importances, it'll just tell you like, okay, PC7 is the most important. You're like, okay, cool, but what is that? And it's harder to figure that out.
Okay, kind of like a random forest, and you have to find the feature names. You're like, okay.
Yeah, and for this, you can't really find your feature names. There isn't really a way to do that directly.
Thank you.
You're welcome. Anything else?
Is PCA used to help with overfitting at any stage?
That's a good question. Overfitting, I think in terms of overfitting, in terms of like over learning your data, it depends on the model. For example, I can see that with logistic regression, if you don't get rid of multicollinearity, you have overfitting. PCA will help with that. Other models, I think not so much off the top of my head. I have to think about this a little bit more, but instinctively, I would say only one of those, only like linear models where multicollinearity could be an issue in your data set. PCA will really, really help with that. But other models that are more about like nonlinear and segmentation, not so much, not so much.
Okay, I gotcha.
Yeah, that's a good thought. I have to think about that for a little bit. Anything else? Cool. I would say for those of you who spent a lot of time waiting for models to run, maybe try transforming your data with PCA. I think that'd be cool to see. For those of you who haven't done your phase 4 reviews, I know about a couple of you here have already done your phase 4 reviews. Could be a cool EDA graph to have. No pressure. You definitely don't have to do that to pass this project, but yeah, I think that'd be cool to see just like overall separability of data. And then you can like encode something like, hold on, let me go back one slide. You get something like this and you can see like, all right, if you have different classes where in like lower dimensionality feature space, everything is distributed. I think that's cool. All right, anything else before we close out for the day?
Just a quick question. Are the class slides lessons are they up on GitHub?
Yes, I put them on GitHub earlier today. Let me just double check. They should be in the phase 4 folder. So PCA, we just have a slide. I think today's is just a slideshow. Next week's there's one that's just a slideshow, but still mostly notebooks. But yeah, all of phase 4 is there now.
All right, thank you.
You're welcome. Anything else? All right, for those of you who haven't yet, don't forget to schedule your project reviews with me. You have until next Friday to finish those out. But yeah, if there's nothing else, tomorrow we continue with clustering, so I will see you all then. And anything else you need, feel free to Slack me as usual. All right, have a good night, everybody. Bye.
Have a good one.
Good night,
Thank
everyone.
you. Have a good night, everybody.
Good night. Good night.